When I was a boy, I did put in a good bit of time making NMR coils. So you'd take a wire and a capacitor and a pencil maybe. I mean, it was just this simple. And then you'd wrap the wire around the pencil and you'd get a beautiful coil coming out here. And maybe you'd want to do just 5 or 6 turns. I don't even know. So for the purposes of this, I have just created an inductor. See? It's beautiful. And I'd put it in here next to my capacitor and then maybe have something else hooked up to it. But what if I just take the two of these up together? Like, I'm suggesting you charge this capacitor and hook it up to an inductor. Now, immediately upon connecting a charged capacitor to an inductor, you would expect that the capacitor would want to discharge, right? And so it would. So let's start us out with a whole bunch of positives right here. Positives. And you want a whole bunch of negatives right there? Well, I can't exactly use black, right? Too late for that. So you'd expect these electrons to go this direction, and well, I guess this plate would become less positive and this plate would become less negative, but the current's going to be going clockwise. And initially the current begins to go clockwise and the inductor says, oh no, I don't want a current in there, but the capacitor just keeps on pushing. And so by the time you've got no charge on your capacitor, we can start us out initially having some charge Q. By the time there's no charge on your capacitor, you've got an enormous flow of current through here. But just as soon as some positive charge begins to accumulate over on this side of the capacitor, that begins to slow down the current going through the inductor. And eventually, as the same amount of positive charge builds up on this plate as was initially on this plate, then the current through the inductor will stop. And suddenly you've got the exact opposite of our initial circumstance. There's no current in the inductor, and there's a charge Q down here and a charge negative Q up here. Let's put a negative Q right there. This is our starting condition, and it will flip, right? And then the current will go this direction through the inductor. Whew. And then it will eventually stop when the capacitor charges back up to its exact original configuration, and it'll go like this, and like that, and like this, and like that, and like this, and like that. And you know this kid likes a good time, right? So let's put him, he likes a keyboard. Let's put him on a ramp that looks like this. And we'll give him something that has very low friction, like, I don't know, a skateboard. Get on that skateboard, kid. And he goes, for a while. And guess what's happening here? He's initially got no motion, but he's got some potential energy stored. And then here he's got maximum motion and no potential energy. We could define it that way anyway. And then he's got no motion. Wait a second. Didn't we say there's some motion but no potential energy? Yeah, I like that. And then up here, he's got no motion again, but some potential energy again. And he's sloshing back and forth between these two things. Do you see that? That's the same thing that's happening with the charge. Initially, the charge is in a high energy configuration, and then it's moving through the inductor really, really maximally, right? And then it's stopped. So this is the same situation. We've got stopped, but big potential energy. And here we've got kinetic energy max, but potential energy 0. And here we've got kinetic energy 0, but potential energy maximum. Okay, so that's exactly the same circumstance as is going on right here. And if I were to draw you a graph, of, I don't know, what do you want to say, charge on the capacitor as a function of time, that charge would go like this. And because Q is CV, we could also expect that this would be the voltage on the capacitor. It would have a very similar performance. We've got positive charge, then negative charge, then positive charge, and then negative charge. But it's not as if, you see, I'm interested in these times here. It's not as if nothing's happening right here. It's like a wave. Oh my gosh, all of physics is coming together for us today. It's like a wave because right here, you don't see the energy in the wave because the energy is in motion. So if you took a snapshot of the situation where this guy's right here, you don't know that he is actually cruising. You can't see his energy. You can see potential energy. You could read off the voltage on the capacitor, but you cannot see when there's a current in there. Because you see, what we're going here is we're going in between electric field in here to a magnetic field in here. And I guess this depends on the way that I've oriented this guy. I'm going to say that this is going up top. So the magnetic field initially comes that direction, and then it sloshes back to the other direction, and etc. And so it's electric and then magnetic and electric and then magnetic. And here we've got potential and then kinetic and then potential and then kinetic, potential, kinetic. And there's this factor of 2 in the frequencies. Oh my goodness. There's so much physics happening right here. Okay, I want to point out, though, that this is simply these two guys interacting. You put some current there, and you say, that's my current. It's going to be the same through both things. And you have them slosh back and forth as they're going around and phasing and all that nonsense. So we've got the inductor and the capacitor. What if, though? What if there's a little bit of resistance? That's what I'd like to present right now. What if it doesn't do this? What if it very gradually dies? So if the voltage in the capacitor is slowly shrinking, then we'll get this kind of performance. And that's, oh my goodness, we have damped simple harmonic motion. That's the exact analogy to friction over here. Friction would cause this guy to make a graph that looks like this. And we could talk about the envelope of decay right here. And we could talk about the time constant of the resistance killing the motion. And we could talk about the same thing right here also. And we could talk about them in terms of phasors. Like, here's the voltage across the capacitor. And it's a phasor, right? And it's going around like this. And sometimes, remember, we have this y-axis. The y-axis is the business end of this thing. And I'm saying right now there's no voltage across the capacitor. Maximum voltage across the capacitor, 0 voltage across the capacitor, minimum voltage across the capacitor. This is what happens if there's no resistance. But if there's resistance, it's as if the phasor itself is shrinking. So we have this spiral inwards where the voltage gets smaller and smaller and smaller, and it hits 0 all the time, but it's spiraling in to the inside. This is friction. It's causing a decay in the overall energy, because the overall energy, I guess, is the distance away from that origin. And that's resistance, and it's friction, and it's in the complex plane. We could say that this is, oh man, what do you want to call this? I guess we could call this potential energy, and we could call this kinetic energy, and it's circling between those two, and gradually energy is being dissipated, so we're going to end up back at the origin, where there is no potential and no kinetic at the same instant. That is the slow death of a simple harmonic system. Let's consider, though, enough of all this awesome, let's consider what's going on if we have an inductor and a capacitor hooked up in parallel. If we have an inductor and a capacitor hooked up in parallel, then, well, I'll tell you what's going on. I'm going to draw you another little sketch here. We've got our capacitor, parallel plates equal size, and we've got our inductor. And these guys are hooked up in parallel, which means that I guess I could say that the RMS voltage across the capacitor is the same as the RMS voltage across the inductor. And the, oh shoot, well this is just IR, but except it's not resistance, it's RMS voltage, or RMS current times the capacitive reactance. And this is the same kind of idea. We've got RMS current times the inductive reactance. All right, and of course we can cancel out some I's. Boom, boom. And what we're saying is if these two guys are hooked up like this, where we've got some C and we've got some L, then I can argue that the capacitive reactance is equal to the inductive reactance. And that means, that means 1 over omega C. Remember, I mean, you should watch this video and really understand why it is this. And this guy is just omega times L. So here's the thing. These guys have opposite or inverse dependences on omega. Capacitors get a lot of reactance when omega is small. And inductors get a lot of reactance when omega is big. This is a beautiful result because I can solve this for omega. If I put omega over here, I find that omega square is 1 over the inductance times the capacitance. So a person like me, faced with this sort of a situation, would certainly end up screwing, and I'd find that the the angular frequency of this circuit, is this circuit simple harmonic motion? Is charge sloshing back and forth? Oh, yes, it is. can we say about the energy that's in this capacitor? What about when there's energy in this capacitor? We could say that the energy is 1/2, I'm going to write it as 1 over C times Q squared, right? And what about this kid who's going like this? No, let's move away from the kid. Let's say a mass on a spring, right? And here's a wall, and here's a spring. It's not an inductor, but it looks like one. Ha, 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 ha. So the spring could be at equilibrium, and it could be moving really fast. Or the spring could be down here, and it could be super stretched. And this energy here has to do with this displacement, and so we could call this energy here potential, and we'd say it's 1/2 kx squared. And this energy here has to do with speed, and that's the kinetic energy would then be 1/2 mv squared. Okay, so I'm going to make connections to these two equations over here. This potential energy is on the capacitor, and the kinetic energy, I think of it as kinetic because it's a magnetic field that's stationary, sure, for that moment. But I'm a charge kind of guy. The charges are moving maximally when the energy is in the inductor. So I'm going to say that this is the kinetic energy in the inductor, and remember that's just 1/2, what was it, 1/2 L times I squared? I think that's right. Oh, dang! This looks like that, right? Look at that, 1/2, and haven't we said that inductance is inertia? Isn't it electrical inertia? Yeah, it's the tendency of the inductor not to let the current going through it change. Okay, so inertia, mass inertia, is the tendency of the mass not to let its velocity change. This is the tendency of the thing to not let this change. That's what kinetic energy is. Check this out. 1/2, 1 over C times Q squared. That's weird. Well, the charge is what's piling up and getting us to have this energy, and K is the tendency of the spring to make it difficult to store, to make it difficult to stretch it. And the capacitance is sort of the inverse of that. Capacitance makes it easy to put more charge on a capacitor. So 1 over capacitance is a lot like a spring constant. 1 over capacitance is a tendency of the capacitor to be really hard to charge up. Much like a tough spring has a big K, a tiny capacitor is really hard to charge up, right? Because, what do we want to say? We want to say Q is CV, and you want to solve this for capacitance, which is charge over voltage. You're going to have to put a really large voltage on something. Well, let's look at 1 over C. Heck, that's going to be voltage per charge. There's going to be a really big voltage per charge if the capacitance is really small. Aha! So that's a spring constant. And this is the same thing. Well, first of all, let me say that this is simply 2 pi times the actual linear frequency of that circuit. So if it's doing something like this, you can find that frequency. Remember, this is going to be your period from here to here, and you could say that, what do you want to say? You want to say that 1 over the frequency is the period, and so you can do all these things. You can actually find things in time that you can use from your omega, where you say that omega is defined as 1 over the square root of L times C. All right. So that was the game back when I was making NMR coils, nuclear magnetic resonance coils. I would change the inductance by actually just squeezing this inductor a little bit, adding another turn, taking away a turn, and change the capacitance by adding more capacitors in series and parallel. All kinds of fun games right there, in order to get the proper resonant frequency for what I was trying to do. It's very important that a circuit have the right resonant frequency, because if it has the right resonant frequency, it can talk to other things. Resonant frequency is sort of like a language of communication, and if you do not have the right resonant frequency, then you don't hear people who are talking on that frequency. It's like tuning a freaking radio! Wait a second, it's exactly like tuning a freaking radio. I have a freaking radio over here, and it happens to have no back on it, so I can show you that this is what it looks like inside of a radio. And there's a knob over here on the front of the radio, and it says tuning. And I'm going to turn that tuning knob, and I want you to see what happens here. Let me see if I can do this in some kind of reasonable way. Look what's happening. First of all, my indicator is moving, and secondly, this is an enormous capacitor, and you will see that it's a variable capacitor, and right now I'm increasing the capacitance because I'm setting those two parts next to each other, and right now I'm decreasing the capacitance because I'm taking those plates outside of the other plates. So changing the capacitance in this circuit by bringing the plates closer together or bringing the plates further apart is causing me to change the resonant frequency, which means that I can pick up different stations. At the broadcast station, they don't want to be able to change that frequency because they say, we're 100.1, the blah, blah, blah. And so they always have the same resonant frequency, and all I need to do to pick it up is to get my capacitance and my inductance in just the right way. So I fiddle with these things. And in the radio, we're kind of inside the capacitor factory, so we can change the capacitance of that capacitor. Oh my goodness, there's so much more to say. I want to connect this omega to the omega that we had for a mechanical system like this. We would say, oh, I'm going to put it over here because that makes a lot more sense. I'm going to say that omega is the square root of, what is it? I think it has something to do with the spring constant and the mass. And I want you to see why this makes incredible sense in the light of this. Because I'm arguing that mass in this equation, the effective mass in this equation is the inductance. And look at them, they're both in the denominator right there. That's awesome. But wait, we don't have a spring constant in the numerator, we just have one. But wait a second, there's capacitance in the denominator. I'm going to say that the spring constant in an electric resonant circuit is 1 over the capacitance. Ding! And if you combine these in just that way, you could just plug them in and get this equation. Okay. I'm going to make it. One final thing that I need to emphasize is this. You know how these reactance equations go. This is the reactance of a capacitor. It's 1 over omega C, and this is the reactance of an inductor, and that is simply omega times L. And what if I ask for the reactive of a resistor? The reactance of a resistor? Somebody would say, Dr. Schuster, that's the stupidest thing I've ever heard. It's simply the resistance. It does not depend on omega in the same way as these other circuit elements do. And I'd be like, yeah, I guess you're right about that. So all of these things, though, combine in a beautiful way to give us impedance. And impedance is this thing, it's like, remember, it's really Pythagorean theorem applied to all of this other business here, except that these guys are opposite each other. Remember when I have an inductor's phasor and a capacitor's phasor? Oh, they're getting a little dirty. I should throw them away. The voltages are exactly opposite each other. So if V is IR, we're going to have one subtracting from the other. So I'm going to say R squared plus, we've got this quantity where it's omega L minus, what am I going to do? Did I want to do this? Yeah, sure. No, I'll do it the other way. Sorry. Omega times L. So this is inductive reactance minus capacitive reactance, and that quantity squared, because we got the resistance, which is in one direction, and the other guys are either this direction or that direction, depending whether we've got more capacitive reactance or inductive reactance. All right. So you put all this stuff. Oh, that's so nasty. I'm sorry. All right, you put all this stuff together and you can make a graph of how impedance changes with frequency. I'm going to put some angular frequency right there. And the first one, the easiest one, is the resistance. So the resistance just goes like that. That is resistance, and it does not depend on frequency. This guy right here is going to be impedance. This is a graph ultimately of impedance, but I've got a lot of other things to graph first. So let me also graph the inductive reactance. Inductors get more and more pissy as the frequency goes up because they really don't like switching, and if you switch often, then they really, really don't like that. But it's linear. It just gets bigger and bigger and bigger and bigger, and this is omega times the inductance, which is the reactive, the inductive reactance. And then we've got this other function. Remember that, well, I guess naturally you've got this dependence on the capacitive reactance starts out really big when capacitors experience a very, very low frequency. They will be really pissy. So it'll be like this. Like that. And this function right here is the capacitive reactance, which is 1 over omega times C. And remember, there's this vector sum of all of this stuff. So I can summarize all of this with a nice blue. Blue will be perfect. And blue is, in fact, going to be the sum of all of these in some kind of complicated way. And it'll come down like this, really close to that function right there. And then it gets a little bit higher. And then it'll go up like this, and then it'll eventually meet that function as the other functions die. Oh, no, sorry, it's got to be a little bit higher because of that resistance there. So, yeah, it'll probably be doing something like that. This is the overall impedance, and the impedance of my circuit has a minimum right here. Where the circuit has the minimum impedance, you want to guess what that is in terms of omega? That is omega resonant. That is the resonant frequency where the impedance is the minimum of the circuit. Of course, you can get the circuit to act at other frequencies. If you've got an inductor and a capacitor, you can have them slash at other frequencies. But if you tune them, it's just like pushing your grandma on the rocking chair, right? You push the grandma at just the right time, and you will get the grandma to be simple harmonic motion. In fact, her amplitude will eventually go to infinity. That is, grandma falls out of the rocking chair, you jerk. Have you no respect for your elders? Don't push that hard. That's fine, but let's consider a graph of the current as a function of frequency, and this will be our final graph. The beautiful thing is, if the impedance, you remember we can make the statement that RMS voltage is RMS current times the impedance. It's like an Ohm's law statement, but it says this is what the RMS values are good for, and the impedance takes into account the capacitance, the resistance, and the inductance of the circuit in a beautiful, well, if complicated way. And I want to show you that if we try to get a current going through this circuit, the current will be maximal where? At the resonant frequency. And it will gradually taper off, and oh man, it has something to do with the inverse of this Z graph, doesn't it? Sure, because IRMS is VRMS divided by Z. Of course it's the inverse of that graph, and of course we're going to have a peak here. This peak is not going to be infinity. It's not like we're going to get an enormous current at that particular resonant frequency. This is omega, what we call it, omega naught, the resonant frequency. I'm going to call that omega naught for you right now. Resonant frequency of the circuit. Now, what is the effect of the resistance here? That's my final concern. The resistance, if the resistance is big, then we're going to greatly increase Z, and that means we'll greatly decrease the RMS voltage, but we don't really change the shape of this graph, although we do a tiny bit. So I'm going to get something that looks like this. This is what happens if the resistance is big. Big resistance. And what happens if the resistance is very, very, very small? Of course, we can't get no resistance at all, but if they get the resistance very, very small, then this Z trough gets really deep. We get way into this. We might also change the resonant frequency a tiny bit. No, we shouldn't if we're actually just changing the resistance. But here's my point. We will get an enormous peak at the resonant frequency if the resistance is very small. And this is tuning NMR coils 101. We want this to have a small resistance, and guess what? This has analogies in mechanical motion as well. You've had a mouthful today. Good luck.